Alright, welcome back to the second part of this presentation. It's again about Boost.Asio, but now about a very specific part about Boost.Asio, about network programming. Told you before, if you were here at the presentation, the first one, that Boost.Asio, even though the library is called Asio, is actually a library about network programming. There are a hell lot of I/O objects in that library which allow you to initiate asynchronous operations around the network. There are, of course, a lot of other I/O objects. I told you there are some examples like accessing the serial port or talking with another process through a pipe. But the topic of this presentation is now network programming. So what we're going to look at is what I/O objects are provided by Boost.Asio for network programming. How are these I/O objects used? We are looking at a couple of helper functions. Most of the functions, or actually all of them we have seen before in the first presentation, were member functions of objects, but there are also some freestanding global helper functions for asynchronous operations. There are a few best practices when it comes to network programming. And then we are also going to look at two source code examples from the Boost.Asio documentation. If you see a complete program, one for client, one for server, just to get an idea how these programs look like. There are quite a lot of sample programs in the Boost.Asio documentation, and you can, of course, spend time yourself, maybe tomorrow, looking at these sample programs. But I know nobody does this, so we're going to do it here together. Again, if there are any questions, interrupt me anytime. Now, if we look at the I/O objects provided by Boost.Asio, we can put them in a couple of different groups. I did this here first in a way that I put the I/O objects together depending on the protocols they support. So we have here a big blue box for TCP, and we see we have here 4 different classes we can use here. I guess that is the protocol most people typically want to use when it comes to network programming. So we have here an acceptor, an I/O stream, a resolver, and a socket I/O object. If you are more interested in UDP, you have a resolver and a socket, and if it comes to ICMP, there's also a resolver and a socket. I think TCP everybody is familiar with. UDP is the unreliable form of TCP, and ICMP is something what you use when you ping another host, for example. So maybe another protocol most people want to use. For this presentation, I'm looking at different groups though, because we have already seen that there are some classes which appear in every group. So there's one group about acceptors, that is TCP only. One group about I/O streams, again TCP only. A couple of resolvers for the different protocols, but there's just one slide for the resolver because all these resolvers are of course more or less the same. There's also one slide for the sockets. Again, we have different sockets depending on the protocol, but again, there's just one slide. Doesn't make sense to look at 3 different socket classes just because of differences in the protocol. Now let's start with the acceptor. The acceptor can be used when you create, for example, a web server. The web server typically wants to wait for clients to connect, and that is exactly where you would use the acceptor. So the acceptor is called acceptor because it accepts incoming TCP/IP connections. So how does this class work? You see the IP TCP acceptor there. I instantiate this class. Again, I pass as the first parameter an I/O service object, which doesn't appear now here on this slide, but you have seen this I/O service object in the presentation before. The acceptor wants a second parameter, a so-called endpoint. There's a helper class provided by Boost.Asio called IP TCP endpoint. It is not an I/O object, there is no async whatever function. Endpoint is just a simple structure, and the endpoint can be used to specify where exactly the acceptor should now wait for incoming TCP/IP connections. So in this case, I use the endpoint to say the acceptor should use the IP protocol 4, and it should use the port number 80, typical web server. Then I call a function called listen. So it depends now on networking, on the knowledge about how networks work. There is typically something called listen. It's not an asynchronous operation, that is the one which I initiated in the last line. That is async accept, and that's where I start to wait for an incoming TCP/IP connection. So I call the function async accept. I pass as usual my handler, the function which should be called when the asynchronous operation completes. That is the second parameter here, and the first one is a socket. So I use another I/O object already of type IPTCP socket, and when the handler returns, and if I assume that there was no error, then I can use this socket to communicate with the client which just connected. So you use the acceptor to wait for incoming connections. Every time you call async accept, you can, if you have a web server, you typically call async accept in a loop because you want to serve many clients. Every time you call async accept, you have to pass a new socket to that function call, because this is then the one representing the connection to the other side, and that's the one you're going to use in the next step to send and receive data. So I'm also going to look now at the socket. Let's assume we just have now our connection to somewhere else, somewhere on the network, and we want now to read some data. You see the socket here, again, instantiated by passing only the IO service object as a parameter to the constructor. And then we can call a function called async underscore read underscore sum. That is the function which we use to tell the socket, okay, please try to accept the data, and when you got some data, tell me, call my handler. And the thing is, if the socket receives some data over the network, it needs to put the data somewhere too. And for that, we need to pass another parameter to async read sum, a buffer. There are many different types supported by Boost.Asio. In this case, I use a boost array here with around 4K of bytes, and this array is wrapped in a buffer function. As I said, you can use many different types, not only boost array, but standard array of course too, or a C array with some pointers. And you can wrap these arrays or whatever you use in that buffer function. You can make it a buffer, you pass it to async read sum, and the function understands that when data is received, it should put the data into the buffer, it should call your handler function, and in your handler you can then access the buffer. What's important to know, the function has already such a strange name, read sum. The function reads some bytes. So when your handler is called, you know you got some bytes, but how much? And you see already, if you check the signature of your handler, there's a second parameter, bytes transferred. When your handler is called, you get the information from Boost.Asio how many bytes were actually received. So when you call async read sum, it could be that your handler is called after 1 byte has been received. It could also be that your handler is called after the entire buffer has been filled with 4K. Most of the time it's a bit unfortunate. Let's say you create a web server and you know the protocol you have to support, HTTP, then you also know already in advance it doesn't help you when your function async read sum is called, when your handler is called, and you got 1 byte. I mean, what do you want to do with 1 byte? And the browser sends you a message and you just receive 1 byte only. So there are some other functions you can use, and as you see, these are freestanding global functions, not member functions. And the one function I use here, it is async read, and you pass now the socket as the first parameter, the buffer as the second, and the handler as the third. And what async read does, async read calls your handler only if the entire buffer has been filled. So within async read,
What is it?
the question was, what is S? S is the socket. Oh, you're right. Yes, it's a good question. Yeah. S should have been a socket as a mistake. If you call async read, you have a loop within async read. So async read is somehow calling async read sum multiple times. And at some point, the buffer has been filled, you got 4K, and then handler is called. And you know at this point, okay, I do not only have 1 byte, I can now access the entire buffer. And if I have, for example, a protocol which I know every message consists of 4K, and I can make sure that I'm not going to work with an incomplete message when my handler is called. There are other helper functions, not only async read. I think there's also async read until. You can then pass a predicate to the function which can actually look at the data which has been received. If there is a certain byte, like an end line, then async read until understands, oh, okay, end of the line, that seems to be now a complete message, let's call the handler now. So most of the time these freestanding helper functions are more useful than functions like async read sum, because as I said, yeah, in the worst case your handler is called after each and every byte which was received. Now a socket cannot only be used to read some data, you can of course also write some data. So you have a similar function here called async write sum. Again, you pass as usual your handler. You also pass a buffer. In this case, the buffer will not be used to put in some data which you received. It will be used to send some data over the network. Again, there are different types supported. In this case, I use a simple standard string, hello world. I wrap my buffer again with that buffer function from Boost.Asio, pass the buffer to async write sum, and yeah, async write sum does its job. What's wrong with async write sum again? Maybe not wrong, but yeah, a bit unfortunate for us. Handler will also be called if, for example, one byte has been written. If only the age of hello world has been written. Normally, we are actually interested in it when the entire message has been written. We don't want to check ourselves, okay, it has only one byte now been written. Do we need to call async write sum again because there are some more bytes to be written? It's all a bit too much work. Unfortunately, Boost.Asio provides us a helper function here too, which is called async write. And before someone asks, S is a socket. Again, it's a mistake. You see a copy of the slide. And again, you pass a socket to that function, you pass a buffer, you pass a handler. And you know now at this point, when your handler is called, the entire string, the entire message has been written. Another I object we can use is the resolver. The resolver can map a readable name like highscore.de to an IP address. For that, use another helper class provided by Boost.Asio called query. Query can accept different parameters. In this case, I put in here two strings, a domain name and a port number, and then you pass the query to the function async result. And async result will not somehow find out what the endpoints are for that domain and for that port. And you see that when the handler is called, you do not get the error code in one parameter, but also an iterator. You can use the iterator to refer to an endpoint, and then you can use the endpoint with a socket to connect to that endpoint. Why is that iterator returned? If I use something like highscore.de and 80 and nothing else, and I have a modern computer, maybe more modern than this one, whose fan is running all the time, then it could be that Boost.Asio detects that your machine supports and the network supports IP4 and IP6. So in this case, you get a couple of iterators, or you get one iterator back. You will just try with iterators to establish a connection to that endpoint. And if the first one works, everything is great. Otherwise, you just increment the iterator, try the next one. And yeah, it can come down to differences like one is an endpoint for IP4, and the other one an endpoint for IP6. There is a question. Somebody wants to have a microphone?
Very quick and obvious question. Why do you use an iterator and not a range? Or put differently, how do I check if there are any more valid iterators available?
Yes, it's a good question. Why there is no range used, I guess it's historic reasons. If there is no other reason not to use a range, you could ask Chris to change that and pass in a range. And you can check yourself whether you have reached the end of the range by constructing the iterator yourself with a default constructor. That is the last one. And what I also want to mention here is not on this slide, but there's again a helper function which you can use, not connect or async connect, but a global freestanding function, async connect, that you can pass an iterator to. And async connect will do the job of iterating over all the endpoints, trying to find an endpoint for you, so you don't need to find out yourself. Does the iterator work? If not, increment it, try the next one. All of this can also be done by app functioning. There's another important thing I want you to look at. The function I call here is called connect, not async connect. So when you think of Boost.Asio, you normally think of asynchronous operations, but it doesn't mean that you cannot call synchronous functions. So in this case, connect blocks until the socket has managed to establish a connection, or until it has failed. And there's no need to use always these async underscore functions. You can actually use functions like connect. There's another question?
How does the handler know stop?
Yes, the microphone coming.
Small question, how does handler know the stop object?
Yes, also a good question. Well, couple of solutions. The easiest one, hopefully you're not going to do now. The stop could be a global object. I do that. What we also can do, of course, when you create a handler, you can use something like Boost.Bind or Standard.Bind. You can pass a local sock object as a parameter to the handler itself. So you typically see here also at this part that Boost.Bind is used to just pass in some more parameters. Next question over there.
Just to make clear, this is the same solution also for read some bytes and so, because they are also don't handle the buffer into the handler.
Yes, absolutely. Also here, that is true. For us here at this point, there we have the array, that somewhere else we have the handler. And the question is again, how do you get access to the buffer from your handler? Again, yeah, global object using Boost.Bind, or of course also lambda functions. Your handler doesn't need to be another function defined somewhere else in the code. The handler could be a lambda function, and I think you have seen it yesterday, and there will be another presentation I think today about lambda functions, where you can then access from your lambda function a local variable like the buffer.
Just another question, how's the lifetime of a buffer managed? So if it just exit scope, but async is just coming in a second later maybe, the buffer object I see whether it's already destroyed.
Then it's your fault.
Okay, so I have to take care of that.
Indeed, yeah.
Sorry for opening this.
No problem, it's good.
I just make a connection to, for example, Node.js or so. When I want to make many parts of different sockets from one handler, and I have always to react to a global buffer or to a global, how did I get the connection between my call or my async read sum and the handler and the buffer?
I see, I shouldn't have mentioned this, in this case, you have a problem if you use only one buffer and you have a couple of sockets and you want to use that one buffer for all the sockets to receive data. And I have only one handler. Okay, that is something you shouldn't do, So in this case, indeed, you should create either a lambda function and make sure that the lambda function uses its own buffer, or you create local buffer objects. You don't create one global buffer object which is used by everyone. You just have to organize the code here yourself. Okay. So there's nothing which is done magically or automatically by Boost.Asio.
Okay. What if these async functions don't return? What if these
async functions don't return? So then can you somehow abort them so that you are sure that you can free the resources, you can free the buffer?
You mean when async resolve doesn't return?
Right, so async resolve usually is calling the handler. Will it eventually call the handler? Will I just wait until it calls the handler? Or is there a way to abort it? Is there the user just close down the program?
Okay, that's a good question, because functions like async underscore whatever never call the handler. These functions always return, and only then at some point we call run on the IO service object, and that one is the one which calls the handler in the end. So a function like async resolve will always return immediately, will never block, it will never make your handler get called, and it cannot fail. Yeah. The async operation can fail, and at that point your handler is called, and that's where you get always this error code parameter, which you normally should always evaluate, and that's how it works.
And the handler is called on the current thread.
The handler is called on that thread, not on that thread, where you call IO service run on. That's another one.
So is it also possible to cancel an asynchronous operation?
Yes, it's possible. These IO objects like a resolver, socket, whatever they're called, they have a cancel member function, and when you cancel asynchronous operations, your handler is called, and then there's a specific error code, I don't know, abort or something like this. Okay. Continue. Right, that was the resolver, and a lot of questions. And there's another IO object I want to look at briefly. Looks a bit strange because you don't see any async underscore whatever functions. It's called IP-TCP IO stream. It's an IO object on a very high level. You can initiate that IO object with something like high score D and a port number, and this object will then automatically connect to that server, to that port number. You can then check whether the connection exists. If here, then you can use that IO object just like any other stream to send and receive data. So it's just a little bit like magic, but in the end, this IP-TCP IO stream object just uses the different IO objects provided by Boost.Asio under the hood. And it's not really asynchronous. Of course, these operations, they only complete when they are done, and there's no handler, but it's just something I wanted to mention quickly. If you want to somehow access other processes on other machines over the network with something like a stream, there is at least something in Boost.Asio which is maybe worth looking at. Now, there are a couple of best practices, and I want to go also afterwards to sample programs from Boost.Asio. Now, some best practices are, I guess, very obvious. Even though I didn't do it in my presentation, you always should check the error codes, of course, in your handlers. What is, I think, also good to do is using the freestanding helper functions, not the member functions like readsum and writesum and whatever they're called, but the other ones where you know when your handler is called, you didn't just get one byte, but maybe the entire buffer has been filled. Then it comes down to using multiple threads. As usual, you have to make sure that you access resources from multiple threads only if these resources are thread-late. And there's only one class in Boost.Asio which is thread-late, that is the IO service class. So if you have a socket and you maybe think, okay, I'll initiate a couple of asynchronous operations on that socket from different threads, not a good idea. There's something else in IO service and Boost.Asio which you can use. There's a post member function which allows you to pass a function through the IO service object to the thread we call it run on. So you can somehow make sure that certain code is executed in another thread. We will see this in one of the sample programs. There's something else which is very important. It comes a little bit back to the question somebody asked before about how do you manage the lifetime of your buffers, for example. You imagine you have an object and you initiated a couple of asynchronous operations and you use member functions of that object as handlers. And there's now something going wrong in one of these asynchronous operations. And the handler says, okay, I don't need that object anymore, I'm going to destroy it. Could be a very bad idea if there are other outstanding asynchronous operations which will then also at some point want to call a member function of the object which doesn't exist anymore. And you typically use something, you see that in a lot of samples in Boost.Asio, you typically use something called Boost enable shared from this. And that is also something we are going to see when we look at the sample programs. Now, if you have internet access and a laptop open, you can follow this on your screen. That is in the Boost.Asio documentation examples. There are quite a lot. And I'm going to look at the chat server and chat client. Which one is the smaller one? Not to shock you. The chat client, I think. Okay, so this is now a complete standard program. Is the font readable in the back, or should I make it a bit bigger? Okay? Right. Now, really simple program. So in this case, we have a... Huh? Okay. I don't have a mouse. Okay, great, thanks. Is it okay? Good. Even more bigger. Simple program, a chat client which you can use on the command line to connect to a chat server. You see how it's used. Chat client calls port. Now we should see a couple of things which we know already. Here's our IO service object. Like every program based on Boost.Asio has at least used one. Here we have a resolver. So the resolver is used together with a query where we pass the host name and the port number to. In this case, the resolver is used to map the host name and the port number to endpoint with resolve, not with async resolve. So we have here a blocking function. The chat client doesn't care whether we block or not, it just waits. Then we get an iterator. We pass the iterator here to a chat client class and together with the IO service object, something we find a little bit higher in the source code. We'll have a look at this in a moment. What else is going on here? Here is another thread created where we call run on our IO service object. So we have now another thread. At this point, the event loop of Boost.Asio starts to run. As we have a chat client on the command line, we also want to enter some data somehow on the keyboard. So we have here a big while loop which reads messages from standard scene. Put these messages here into the array. Then there is a chat message created. That is a class we're not going to look at. It's a very simple one. A chat message consists of a header and of a body. And in this case, we just copy here the line which has been read from standard scene into that chat message object. So we set here the body, we encode the header. So these are details depending on whatever protocol is used here. And then we access our chat client and we write the message through the chat client to the server. At some point we're done, we can get out of this loop anytime with Control C. Then we close the connection to the server. We wait for the thread to finish. T-join. At some point run returns. I told you also in the first presentation, run returns when there are no outstanding asynchronous operations anymore, and the program is done. Now, how does this chat client look like? We said we pass here an IO service to it, a service object, and an iterator to the endpoint. So let's have a look at the constructor. Here's the constructor, the IO service object. We get here the endpoint. Here we see we use one of these freestanding helper functions in Boost.Asio, Boost.Asio Async Connect. It was a function I had mentioned before. We pass here the endpoint iterator to that function, and that function will automatically find out whether the first, second, third, or maybe another iterator works. It can be used to establish a connection to the server. We also have to pass a socket here to Async Connect. That is the one which represents the new connection. The socket is a member variable here of the chat client. And what else do we pass? Here we pass our handler. And we see here that, I mentioned this before, at this part we very often use boost bind. In this case we have to use boost bind because we want a member function here of our object to be used as a handler. Another global function, but we have to pass in also the sys pointer somehow, and that's how it works. So at some point the connection has been established. Then handle connect will be called. Handle connect is a member function here. So, first best practice, we check of course the error code. If there's no error, we start to receive data over that connection from the server. Maybe there are other people using the client, they're going to write something, so we always want to have an asynchronous operation which can receive data over that connection. So we call Boost.Asio read. Again, global freestanding helper function, pass in the socket, pass in here our buffer. Read message is, let's see what this is. Must be another member function down here. Okay, it's a chat message, and this is other class used by the client server application which we can ignore. As I said, it's just a header and a body, something very simple. So we read in here the data, we have the buffer used, and again, we need a handler, and again, we use Boost.Bind because our handler is a member function of this object. So at some point, handle read header is called, that is this function here. Handle read header checks whether there has been an error or not. If there has been no error, the header is decoded. So stuff is going on here has nothing to do with Boost.Asio, whatever Chris decided to do here with the messages. Then again, async read is called. Why async read called again? We just got the header of the message. We still need to get the body following the header. So we call again async read. We still need to read data coming in from the same connection. We still need to use our buffer. Here it was read message data for the header. Here it is read message body for the body. And then, if that works out, handle read body is called. Here is handle read body. If there has been no error, we know at this point we got the header and we got the body, so the message is complete. And now we can write the message which we got from the chat server to standard cout. And then afterwards, there can be of course more messages being exchanged between all the clients, so we need to repeat the whole thing. We call again async read the socket, we go back to the handler which we had looked at first. It's of course an endless loop. It's always the header, the body received, everything is decoded, sent to standard cout, and the whole game restarts. When we type something on the keyboard, we also want to send the data to the server, and we have seen down here in the main function in the loop that we call cWrite and pass in here the message we created. Now this message has to be passed somehow to the socket. And when we look at this write function, we see that we do not simply access the socket and call write or async write, but we call here a function called post on our IO service object. That was something I had mentioned before on the slide, and it is important that post is called here, because the loop which we use to read data from the keyboard is executed in the one thread, and Boost.Asio and all the IO objects which are used here to communicate with the chat server are used in another thread. That is something you have seen here down in main. We want a thread created to make IO service run. That is done in another thread. And in the primary thread, that is where the loop is run and executed to read data from the keyboard. Now I need now to pass the data I got from the keyboard. I need now to pass this data to the other thread somehow. Not that I access the socket to write some data, and that the socket is used at the same time by a handler to read some data in the other thread. And then I probably have a question. So I have to make sure that I pass now the message from the one thread to the other one. And before you start thinking about user access and everything else, don't forget that there is this very handy post member function which you can call on the IO service object. What you do here, you just say to post, please execute a certain function in the thread you own. In the thread I called run on before. So what happens here is we say call the function do write and pass the message over here to that function. And do write, is it here? Do write is executed now in the one thread the IO service object owns. So when this function is executed, it is clear that there is no other handler executed at the same time. So in this function we can now access the socket. The socket is one of the many IO objects in Boost.Asio which is not thread safe. Don't forget the only thread safe object is the IO service object. So at this point it is safe to access the socket and write some data And that's how this client works. And let's have a look at the chat server. The chat server is a bit bigger, which I think is easily understandable, given that the server needs to manage a lot of connections to many, many clients. So they can, of course, a lot of clients connect. Now let's have a look how this server works. Of course, we have an IO service object again. And then what do we have here? We have a loop. We can actually ignore the loop because you can use the chat server with many, many different ports. So just think about, we use the chat server now with only one port. So we can ignore the loop now. And we have only one chat server, so no point to look at this loop here at this part of the program. Where is it now? Here is our chat session. Now that is the chat server. That is the part of the program which has to manage the different clients. And somewhere we should actually see acceptor. Here is it. Chat server. Here is our acceptor. That is the IO object which waits for incoming connections. So it is used by the chat server. The chat server has its own acceptor. Is it? Yeah. It's here a very normal member variable. And when the chat server is started, it calls start accept. That is the member function here. And start accept, calls the async accept function. At this point, I initiate the asynchronous operation. I want to wait for incoming TCP/IP connections. And when async accept returns, when the asynchronous operation has been completed, my handle accept member function is called. What does handle accept do? It starts the session. The session is another class in that program where the socket is used. The socket which represents the connection to the new client. And once I have accepted a connection, I just start to accept the next one. Rather normal server, just always calling accept, accept, accept again. Whenever a new connection comes in, that socket is used here within that chat session class. So Chris decided to create another class here to represent the connection, to represent the session with the client, and that class chat session has, of course, a socket. Here's the socket, and this class should be called chat session. Chat session. And what's going on here in the chat session? Well, it's very similar to the chat client. The chat session needs to read and write data again. So we access the socket here. So when the chat session is started, when the connection has to be established, we always want to wait and accept some data. We always want to read some data. So we call async read on the socket. We use here again our buffer. And when read has been called and we got some data, handle read header is called. Where's handle read header? Handle read header is here. If it hasn't been an error and we could decode the header, we call async read again to read after the header the body. You see it's very similar code as in the client. At some point the body has been called. Then the message is delivered to a room. Another object here used in the server. The room has pointers to all the chat sessions in the server. So just make sure that the message which has been received here is sent to all the clients. And then the game repeats again. We call again async read to read the header of the next message. There's one thing which is important here, because we have at this point multiple outstanding asynchronous operations, at least maybe. There's one outstanding operation always, because we always want to read something. There's always some async read function called. When you just got the header, you call async read to get the body. When you just got the body, you call async read to accept the next header. So there's always an async read function outstanding. Sometimes when you got some data, you want to send it to everybody else. So there must be also a send function or a write function. And you see this here. Here's a handle write. Here's somewhere else async write used. So it could be that there are outstanding asynchronous operations for one chat session object. One to read something, another one just waiting for a write operation to finish. Now we have to be careful if we have a couple of outstanding asynchronous operations. If you imagine one of these asynchronous operations fail, and we know we can't use the session anymore because, for whatever reason, the connection didn't work anymore, and we decide to delete the object, then we could have a problem when the second asynchronous operation completes, because we always use member functions of this object to complete the operations. So we have to make sure that this object is around until the last asynchronous operation has been completed. Not that one of these operations deletes the object and the next asynchronous operation completes and the handler says, well, great, segmentation fault. And what we normally do here in Boost.Asio, when we create these objects on the heap, when we use new to create the objects, we use a shared pointer and we use in our parent class enable shared from this. Not sure whether you are familiar with enable shared from this. You can also look it up, of course, in the Boost documentation. It's a class from Boost. Enable shared from this provides the object of type chat session access to its own shared pointer. And when you initiate asynchronous operations like here, async read, you don't pass this as a pointer, you pass the shared pointer here at this point. And as the shared pointer is passed now here to Boost.Asio, to the IO service object, it doesn't matter whether another asynchronous operation is going to fail, whether another synchronous operation is basically making sure that the other shared pointer is going out of scope and that the short pointer reference is going to be decremented by one. There's always a shared pointer somewhere in the IO service object if there's an outstanding asynchronous operation. And only then, when all the handlers are called and all the handlers realize there's always an error, and there's no point anymore to initiate a new asynchronous operation, then all these shared pointers go out of scope, the reference count is decremented until it's 0, and when the last asynchronous operation has been completed and does not initiate another asynchronous operation with the shared pointer, then the object of type chat session is automatically deleted. You have the end anyway, and then now there are a couple of questions.
If we give an async operation to the IO service and it reports by columnar handler, doesn't that mean that the IO service just lost the last async operation that it had to do, and should it finish actually? Should we always have a work in IO service, because when it finishes you can't just, you created another connection, but didn't IO service just finish because you didn't have any other?
Yeah, it is true. This only works out if there is an outstanding asynchronous operation. Otherwise, the IO service object would run out of work and would return and wouldn't call the handler anymore. But if you don't have any handler anymore to be called, if you don't have any asynchronous operation anymore anyway, then there is no shared pointer, you don't need the object has been deleted already before. So the trick here is, if you use member functions as handlers, and you have maybe a couple of outstanding asynchronous operations, make sure that you don't add in somewhere delete this. Because then, not that you are going to cut off the branch you're sitting on. So make sure that at this point you think of using a shared pointer or somehow a reference counter. And what is used very often in these samples is Boost shared pointer, and then this class Boost enable shared from this. And as you pass all the shared pointers around, the handlers make sure themselves with the shared pointer that when the handler is called later, that the object still exists. That's the trick here.
Since shared pointer capability is also available in this kind of native shared from different.
Okay, yeah. Good contribution. I have one last slide again, a couple of links in case you want to read a little bit more about it. Again, Boost.Asio documentation, then there are really a lot of examples. Given that there are a lot of IO objects in Boost.Asio, we have only looked at 2 examples now. There are many other examples where you can see how the different network IO objects are used. There are also some very sophisticated classes, like you want to use encryption with SSL, even that is in Boost.Asio. Again, here the link to the chapter in my online book. And there's something else based on Boost.Asio. An attempt to provide access to network functions a little bit easier, something called URDL, or how do you pronounce it? Okay, but there's another paper here. I think this paper has also been written by Chris, and yeah, these are ideas how to put network functions into a future C++ standard. Does not necessarily have to be based on Boost.Asio, because other people want to access maybe classes which are easier to use, maybe something like the IP TCP IOStream class, which look very simple. And yeah, there are different ideas, different thoughts, so maybe that's another interesting paper to read. And we're done at this point. If there are still any questions, I'm also here to answer them. Otherwise, yeah, enjoy the rest of the day. And we'll have a day.
Do you see some use of ASIO with messaging libraries like, I don't know, ZeroMQ or TP and so on?
I know that there are some people who I would describe as Boost.Asio fans. They spend a lot of time creating extensions for Boost.Asio, playing around and seeing whether Boost.Asio can be used for many other things. I've explained already that you can use Boost.Asio together with REST, and there are also some features implemented in Boost.Asio, like passing a function from one thread to another somehow. And I know that there are some people who created some more extensions somehow, managing threads by I/O objects. Doesn't really have much to do anymore with asynchronous I/O. But I haven't heard anything about connecting Boost.Asio to other frameworks like Qt. But I think I would recommend you having a look at the Boost.Asio username list. And there are some people who write a lot of messages there, and these are the ones who are normally also very active creating extensions.
Thank you.